Lecture 1 covers sections 1.1 through 1.3. At the end of today's lecture, you should be able to determine and understand basic SI and US customary units and how to convert between these two unit systems. You should also be able to understand and apply prefixes to units. And lastly, you should be able to understand the importance of significant digits and how we handle significant digits during mathematical operations, such as addition, subtraction, multiplication, and division. For us to begin, let us talk about this course. Now, mechanics can be broken down into three categories. These categories are rigid bodies, deformable bodies, and fluids. Within the study of rigid bodies, we have static systems, which aren't moving, and we have dynamic systems, where movement is allowed. And under the study of dynamics, we have kinematics and kinetics. Now, when we talk about deformable bodies, we're talking about mechanics of materials. And lastly, when we talk about fluids, we're talking about compressible or incompressible fluids. Now, the focus of this class lies on sections 1.1, statics, and sections 2.1, mechanics of materials. However, the content we learn within this course is going to be applicable to all aforementioned topics, and you're going to see a lot of similarity between what we derive in this class as to what's expressed in fluid mechanics and dynamics. Now, let us begin. We first have to talk about units. Any physical quantity can be characterized by using a unit system, and we have two unit systems, the SI unit system or the US customary unit system. Now, this physical quantity is going to have a numeric value that represents its magnitude and units that define its dimensions. Now, each of these systems, the SI and US customary, is going to be based upon a set of primary or fundamental dimensions for which we derive all other dimensions. All other derived dimensions are referred to as secondary units. Now, we have our four basic dimensions: length, mass, time, and temperature. In the SI unit system, length is expressed in meters, and we express this unit as m within square brackets. The square brackets indicate that this is a unit, not a variable. Mass in the SI unit system is a kilogram, represented as kg within square brackets. Time is expressed as seconds with an s in square brackets, and temperature is expressed as degrees centigrade. In an absolute temperature scale, we will use degrees K, or Kelvin. Now, in the US customary system, length is described by feet, where a foot, ft, within square brackets, defines our length. Mass is denoted as pound mass, and we have lb with the subscript m within square brackets. Now, this is going to differ from pound force, which has an f in the subscript. Time is the same, where we have seconds, and temperature is described in degrees Fahrenheit. In an absolute temperature scale, we would use degrees Rankine. Now, derived units are very important. These units are based upon fundamental quantities and are able to express more complicated terms. The most common derived quantities in this course are as follows. Force. Force is the description of the action of one body onto another, and we can have surface and body forces. Now, force is described as mass times acceleration. So the variable F represents force, and this is going to be equal to the mass of a body m times g, or gravitational acceleration. Now, mass has units of kilograms, and gravity has units of meters per second squared. Thus, force has units of kilograms, meters per second squared. And force is described with a unit of Newton, a capital N, within our square brackets. Now, area is simply length squared with units of meter squared, and volume is length cubed with units of meters cubed. Now, the last main derived quantity we have to talk about is pressure or stress, and this is force per unit area. Pressure, denoted by the variable P, is our force per area, or a Newton per meter squared. And the unit associated with pressure is a Pascal, capital P, lowercase a, within our square brackets. Stress has the same formulation, and all we have to do is replace P with sigma. Now, let us look at example 1. Say we want to determine the following derived units. So, what are the base units of acceleration? Acceleration is equal to time rate of change of velocity, or we'd have d by dt of meters per second. Now, since we have d by dt, we're differentiating with respect to time, so we could replace this as a 1 per second. If we multiply this through, acceleration has units of meters per second squared. Now, energy is expressed as force times distance, and this has units of joules. We want to express joules in our base unit. So a joule, represented by capital J within square brackets, is our force newtons times our distance m. A Newton is a kilogram meter per second squared, and if we multiply this through by meter, we then have joules expressed as kilograms times meter squared per second squared. Now power is the time rate of change of energy, and it has units of watts. Say we want to express this in our base units. Now a watt, a capital W within our parentheses, is a joule per second. Our joule we found to be a kilogram meter squared per second squared, and if we divide this by second, we'd have kilogram meter squared per second cubed, which describes the base units of watts.